All right. So one big component of this first thing was finding domains and ranges. And remember I said I had my mathematical commandments. There are only 3 of them. It's easier than real commandments. So you cannot divide by 0. You cannot square root negatives. And you cannot log negatives or 0. Those are the 3 things, okay? And that's because of the domain of the log function. Log functions look something like this, and they never actually cross the y-axis. The last one's the trickiest one because you're at least familiar with logarithms. Okay, and if those things are, if you have a combination of square roots and denominators and logs, you've got to account for all of those rules. None can be broken. It's like for this first one, there's one number that x cannot be. X cannot equal 1. Where does that come from? That comes from the denominator. Okay? So you've taken, so just keep that like in your back pocket, think about it. The rest of it is that the stuff inside the square root has to be greater than or equal to 0. That's what it means to be positive. So that means x is bigger than or equal to -5. Does that make sense? And you can test that by plugging numbers in. Like if you plug in -6 for x, you get a negative inside the square root sign, and that's not possible. You can't do that. But as long as numbers are bigger than -5, you're good. So I'm going to graph this to give you a sort of a visual representation of what we're looking at. From -5 on up, everything's good, except for you've got to leave one number out. What number is that? 1. So you have to take that number out of there. So how would you take that picture and make it into an interval? Would there be a square or open bracket at -5? Square. And the way you say don't include 1 is you do 1, you put a parenthesis, union, 1 to infinity. If that 1 had fallen outside of the interval from -5 up, like say it would come out to be like -10, would it matter? It wouldn't. If this had come out to be -10, -10 would fall to the left of that -5 point, and it already would have been excluded. Does that make sense? Okay. All right, this guy. So the basic setup is you're solving the inequality x squared plus 7x minus 18 bigger than or equal to 0. So what's the first thing you think to do? Factor. I like that. Factor. You get x plus 9. Okay. X. Okay. Solving inequalities does not work the same way as normal numbers. Okay, so here's what some of you guys did in your test. You said, okay, x plus 9 bigger than or equal to 0, x minus 2 bigger than or equal to 0, which is not completely wrong. Okay, that means that if those two numbers, the x plus 9 and the x minus 2, are going to multiply to make a positive, then they both have to be positive, right? That makes sense. So this one says x is bigger than or equal to -9, x is bigger than or equal to 2. And so if you're accounting for both of those things, from -9 up and from 2 up, what works for both? Works for both. Is it from -9 up? No, where does it start? It's from 2 up. Now here's the problem with that. Two numbers multiply to make a positive if they're both positive, or if they're both negative. So technically speaking, if you want to do it this way, you've also got to solve x plus 9 less than or equal to 0, x minus 2 less than or equal to 0 as well. You see why that's true? I'll show you this way because a lot of you like kind of go this way without me telling you that it's true, and you miss half of it. So x is less than or equal to -9, x is less than or equal to 2, and you have to have both conditions met because they have to both be negative to multiply to a positive. So that's from -9 down, 2 down. Where are both conditions met? Give me as an interval. -9 is where they start to both be met. So -infinity to -9. So the answer would be -infinity to -9. Those numbers work. and 2 to infinity. Everyone that did it this way, when they did their test, missed this part of it. Because nobody thought, oh my gosh, if two things multiply to positive, they have to either both be positive or both be negative. I showed you a different way because I think my way is easier. I said that this is a parabola, right? Where does that parabola cross the x-axis? Where is it equal to 0? -9 and 2. And then is it a happy parabola or a sad parabola? It's a happy parabola, right? So it does something like this. The specifics of how far up or down or go aren't really important for us right now. And you're looking for where that parabola is positive, right? That parabola is positive, or the y's are positive, when the function is above the x-axis, right? Notice how that's the same thing we have down here. Does that make sense? So I want to take the chance to show you guys this way in case you do it that way. But I think if you can think, oh, I should look and see where this thing is positive looking at a graph. What was another way we did it? We did the little number line thing, right? You plot -9, you plot 2, and you test some points, right? And you're going to get plus, minus, plus. So I think that these two ways are probably better because in addition to being more generalizable, like they'll apply to stuff that you can't, especially the number line applies to stuff that you can't graph very easily. Does that make sense? Also, they're shorter. You agree with that? Okay. So we'll do some more number line stuff later in this review, but does that help a little bit? Okay. Alrighty. This is like a calculus question, okay? So you have to know what this stuff means. So what does f of x plus h mean to do? Think back to what does f of 3 mean? Replace all the x's by 3. What does f of 10 mean? What if I gave you f of banana?
Bananas.
You put in bananas for all the x's, okay? I know that's goofy and silly, but that's what you would do. So what do you put in for all the x's if you're just asked to find f of x plus h? You plug in x plus h for everything else. It replaces the x's. So that becomes 4 plus 5. That x is replaced by x plus h. This x is replaced by x plus h. So that part corresponds to this part. Minus. If you want to take away the whole function f of x, do you do this? You put parentheses, yep, exactly. And all over h. Now this problem is just like algebra on steroids, okay? It's just like crazy lots of simplifying. You have to not lose stuff. You have to write legibly enough you can actually read it. 4 plus 5x plus 5h. Real quick, what is x plus h squared? Spectacular. And then minus 4 minus 5x plus x squared. All over h. And if you're going to cross off stuff that cancels on your test, do so very lightly so I can still see what you had there. I once had students scribble it out so I couldn't see what they had, and that was very not helpful. So what cancels that you can tell right away? The 4s, What else? 5x. And technically the x squareds are going to cancel once that negative distributes, right? Okay. Alrighty, so then what we have is 5h minus 2xh minus h squared, all of that over h. Does that seem right? And now because every single term has an h, you can divide every single term by h, and what do you get? Perfect. 5 minus 2x subtract h. Okay. So tell me whether these following functions are even, odd, or neither. You must show your work for full credit. So how do you check for even and oddness? What do you plug in? Negative x. And you guys have gotten pretty good at this because we did it with sine and cosine again. So by now you're like rock stars. 1 minus 4 times negative x to the 6th. And what happens if you take negative x multiplied by itself 6 times? Is it a result of positive or a negative? Positive. So you got back the original function. That means you're even. So when I say you have to show your work, you've got to show me that you know that checking for evenness and oddness means plug in negative x. Once you've passed this class, you can just do this in your head. Does that make sense? It's the rite of passage. You must get past me first. Ha, be scared. All right, negative x cubed plus 2 times negative x plus 1. So will the result of cubing negative x be positive or negative? Negative. Next one will also be negative, and the 1 stays positive. Okay, so it obviously didn't give us back the original function, so it's obviously not even, right? Did it give us back negative the original function? No. Why not? What messed up? The plus 1. Does that make sense? So this is not equal to g of x, which means it's not even. It's not equal to negative g of x, which means it's not odd. So it's neither. Does that make sense? Okay. In general, if you have odd powers and you add a odd number, any number to it, that's never going to be odd again. But with an even function, and you add a number to it, it'll still be even. You can think about even graphs have that y-axis symmetry. If you shift them up or down, they still have y-axis symmetry. Odd functions have symmetry about the origin. If you shift them up or down, they lose that symmetry. Unless they're very special functions. But I can't think of any examples where you would retain that. Okay. This is one thing that I think completing the square is super, super useful for, is graphing parabolas. So putting them back into vertex form makes graphing so much easier and faster. Okay, so we got x squared plus 6x. What if you looked at this problem and I said complete the square, what would you do first? Is there anything you would subtract the 5? Sure. If not. The thing is that don't say the equation's equal to 0 because it's not. Just leave the f of x there. Does that make sense? Okay, so f of x minus 5 equals x squared plus 6x. And then what number do you add to both sides? 9. So that's f of x plus 4 equals x plus 3 squared, right? Okay, and what's the next thing? Subtract 4. Perfect. So then this is a parabola shifted left or right, and how much? Left 3 and, okay. And once you know that, you just have to get the points that the parabola goes through correctly. So I'm going to start by graphing just x squared. And this should be super easy. What does x squared go through?
Origin.
The origin. What other point? 1, 1, and also negative 1, 1. The next point is 2, 4. A lot of you got that the third point we just graphed incorrect because you didn't put it up far enough. Does that make sense? You had down one too many? All right, and then shift that thing how? I'm sure I said it right. Left 3 and down 2. 4, sorry. 3, 4, can't count. And then get the points in the right spot. Notice how those points that were right there, they landed on the x-axis, right? There you go. Good enough.
If say it didn't say find the vortex work, could you just factor it and then
You could,
points?
yeah, you could factor it and you could plot the intercepts and you could just plug numbers in. That would also work. But the thing is that I could also give you something that did not factor.
Yeah.
Like if I had given you x squared plus 6x plus 3. But you're totally right that if you say set this equal to 0 and you found the x-intercepts, that's a completely legitimate way to graph it as well. Yep. The only problem with plugging in points randomly is it's hard to know where to start. Does that make sense? It's like if you start by plugging in 1, you're gonna get like really big numbers, right?
Well, I mean, you already know that they cross the x-axis.
If, that's what I'm saying, like if you know where they cross the x-axis, then it gives you a hint as to where to start picking.
Yeah.
Does that make sense? So in that case, you're definitely correct. Awesome. All right. Jessica, did you get a copy of these? You're all allowed to come pick them up. I'm not gonna be mad. It's totally fine. At least you came. So find the inverse of this function, give the domain and range. All right, so how do you find inverses? What's the first thing you do? Swap x's and y's. So that'll be x equals y minus 1 over 2y plus 5. Does that look kind of familiar?
It's your favorite.
Didn't we? That's my favorite because you guys need to learn it. Didn't we do it yesterday?
Yes.
Yeah, okay, so see if you can do it, like, now. Go. Did anybody get negative 5x minus 1 over 2x minus 1? It also is correct if you got 5x plus 1 over 1 minus 2x. If that, because that's just by multiplying the denominator and numerator by negative 1. Okay, so there's the inverse. Now, give the domain and range. So for the domain of f inverse, what's the one thing x cannot equal? 1/2. How is the range of f inverse found? What do you look at? Look at domain of f. Remember how they flip-flop? So what's the one thing that y cannot equal? Negative 5/2. It's the number that makes the denominator of the original function 0. That's the relationship, and that really is the best way to find the range. So what I was testing when I asked that question of you guys was, do you know that's the relationship, basically? Interval notation? Was your question if I require you to, or what would it look like if you did? If you did write it in interval notation, the first one would be negative infinity to 1/2, union 1/2 to infinity. And the second one would be the same thing, negative infinity to negative 5/2, union negative 5/2 to infinity. Does that make sense? Okay. Awesome. Good? Okay. Ooh, long division. Can I go back? Yeah, of course I can go back. All right, dividing. All right, so rewrite this as with long division. So who goes outside the check mark, who goes inside the check mark? I thought that makes sense as a question. Do you know what I mean?
The denominator goes on the outside.
Yep, 2x minus 3 goes on the outside, and you're dividing that into 6x squared minus 17x plus 7. Okay. And then you think, what do you multiply 2x by to make it match that 6x squared? And what is it? 3x, right? Does that make sense? Then you get 6x squared minus 9x. The one place this gets tricky is you have to now take this away, and you've got to watch out for double negatives. So if you're going to one textbook that I used, or did is it wrote down inside the parentheses what the actual sign would be once the negative was distributed. Don't be like my high school students and cross off that minus and make it a plus. What is one reason doing this could be bad? And I think you also lose track of what it was in the beginning. Does that make sense? So don't do that. That's terrible. Shame on them. I had to beat that out of them. Failed, but I tried. So we're actually doing negative 17x plus 9x. So what does that make? Negative 8x. And then you think, okay, what do you multiply 2x by to make it match negative 8? Negative 4. So negative 8x plus 12. Take it away. That actually is a minus. So 7 minus 12 is negative 5. Okay, if you think about regular division, like if you say 2 goes into 7 and it goes in 3 times and has a remainder of 1, that's 3 plus a half, right? Same idea, same exact idea here. What number in this problem corresponds to that 3? Or what numbers? Mm-hmm. And then, yep, exactly. And actually, there's a way to check this if you have the time to do so. You could take this thing and get a common denominator. Do you see what I mean? Like multiply either the whole 3x minus 4 or 3x and negative 4 individually by the denominator of the last part. What should you get when you simplified it and added it all together? You get that original thing back, right? So that's how these two things are connected.
Does it matter if you mean the negative sign in front of the 5 big, does that matter?
You'd have to do something like 3x minus 4, you could say plus negative 5 over 2x minus 5 is also okay.
Okay,
Does that make sense?
Be a sign.
There needs to be a sign between them, because if there is no sign, it means multiply. Does that make sense? That's the default sign in math. So no sign means multiply. If you don't mean multiply, put something else there. Awesome. Okay. All right, so we're on to inequalities now. So here is where a lot of you made mistakes, and I'll try to explain why they went wrong. Okay. Some people divided by x. That has a couple issues. First of all, x could have been 0. Also, x could have been negative, and how do you know? Does that make sense? Because if x was a negative number, the inequality sign flips and everything changes, right? So don't divide by variables, okay? Just don't do it. So start by making this somehow related to 0. I'm going to do x cubed minus 4x less than 0. And the idea there is you're going to make a number line and you're going to test points and stuff. So now factor the expression on the left-hand side. First thing is there's the greatest common factor of x. And then how does x squared minus 4x factor? X plus 2, x minus 2, or vice versa, it doesn't matter. And now I am definitely making a number line here. And you're going to use this in calculus to figure out where functions are increasing and decreasing, so we're going to check the sign. Okay, so first plot the zeros. There are zeros at 0, and at positive 2, and at negative 2. And you pick your test points. So what's a good test point for over here? Negative 3. And it actually, you can plug the test point into like any of these steps, but it's often easiest to plug the test point into the factored step because it's easy to determine the sign of each factor individually. So if you test that negative 3 in the last step, the first factor is negative, right? Second factor is, and the last factor is also negative, right? So overall we are negative there. If I test negative 1, first factor negative, second factor, last factor negative. So overall you are positive on that interval, right? 1, positive, positive, negative, right? So overall you're negative there. And past 2, say testing 3, we're just one big fat plus. Okay. And then you've got to ask yourself, which intervals were you looking for? So since the original thing that you were looking at was this thing is less than 0, you're looking for where this thing is so negative. So, and also not equal to 0, so you don't include the endpoints. So from negative infinity to negative 2, and where else? 0 to 2. Okay, great. Would it have been wrong to do it like this? No. You're just going to then be solving a slightly different expression, right? And it would factor into x, it'd be 2 minus x, 2 plus x, okay? And you'll do the number line analysis with this thing, and you're just gonna be looking for where is that expression positive instead. So, and you'll get the same conclusion as long as you don't make little errors along the way. The most important thing is don't divide by variables, okay? If you can't divide by variables, you probably shouldn't multiply by them either, right? That was the biggest mistake on this one, is that you multiplied by x, and that ends up messing a bunch of stuff up. So here you have to move the 1 over. I think this is the easiest way. And it's always easiest to reference these things relative to 0. And on the previous one, we factored, what could you do to make the expression on the left-hand side of what I've got there simpler? Common denominator, yeah. 2x plus 1 over x minus x over x. So that would be x plus 1 over x bigger than or equal to 0. Okay, so then make your number line, and numbers that get plotted on this number line are 0, so you have a 0 at negative 1. What other kind of thing do you have here? You've got a vertical asymptote at 0. And that vertical asymptote is kind of the thing that's lost when you multiply by x, is you lose the fact that it's a vertical asymptote. And the point is that certain functions, like we've had pictures of stuff that have asymptotes, and they do this kind of thing, right? They change positive and negative at asymptotes. They don't have to, but they can. Okay, then test some numbers in this simplified form. So say if we tested like, I don't know, negative 2. The numerator will be negative, right? And the denominator will also be negative, so overall you're positive there. Do you agree? Okay, have to test a fraction, so negative a half. Run for cover. Numerator, denominator. So positive over negative makes negative. And then past 0 will be big fat positive. Okay. And the one tricky thing here is that you're looking for where this thing is bigger than or equal to 0, right? So do you include negative 1? Yes, so negative infinity to negative 1. Do you include 0? No. Why not? This is a vertical asymptote. Woo! Can't trick you. Good. I don't really want to trick you, so don't let me win this game. Okay. So find all vertical asymptotes, all horizontal asymptotes, and if there are none, state this and give a short explanation as to why this is the case. Okay, so first of all, vertical asymptotes. Those happen where x squared plus 4 is equal to 0, right? Which means x squared equals negative 4. Never happens. And that's what I mean by give me an explanation. You know, you just say x squared plus 4 doesn't ever equal 0. There are no places where the denominator is 0. Does that make sense? That's what I was looking for. So what were the rules for horizontal asymptotes? What do you look at?
Largest x.
Look at the largest x powers. So that'd be 1, and officially, if it's a horizontal line, is it a y equals or is it x equals?
Y.
Y equals. So that what this means is that as you plug in bigger and bigger and bigger x's, you're going to get closer and closer to a horizontal line, y equals 1. You could plug this into a graphing calculator or a graphing app, and you're going to see that in this picture. As you zoom out, this function flattens out.
How did you get the horizontal asymptote?
The way you find the horizontal asymptote is you take the ratio of the largest powers.
Oh, yeah.
Remember that? So make a note to yourself, you look at the x squared over x squared, and that equals 1. We'll talk about how to deal with that if you have different sized powers as well. Okay, for this one, vertical asymptotes happen where the denominator equals 0. Does that have places where it equals 0? Mm-hmm. Take out 2x, x plus 4. So where does that equal 0? Mm-hmm. 0 and negative 4.
Wait, at the vertical asymptote, if we would have solved it, sorry for the previous one, for
Mhm.
x squared plus 4, and would we have gotten positive negative 2?
Oh, you would have had imaginary things. Because x squared equals negative 4.
Oh, okay.
Right? And so if the denominator had been x squared minus 4, then yes, they would have been plus or minus 2.
Okay.
But since it's x squared plus 4, and the only solutions that are imaginary answers, there are no real numbers that make that happen. Okay, so for horizontal asymptotes, look at the biggest powers. What's the biggest power in the numerator?
X cubed.
Mm-hmm. And how about the denominator?
X squared.
And we'll just take the 2 to be safe, 2x squared. So if I reduce that, I have x over 2. And here's the slight issue. What horizontal asymptotes are is it's what's occurring as x goes to infinity, as x gets huge. So does this approach a number as x gets huge? No, it just gets huge, right? So in that case, there are none. You see what I mean by that? Okay, there's officially a slant asymptote, but that was a special thing I went over because I just wanted you to see it. I'm not going to put that on your test. Officially, the line, I'm not sure if that would be the slant asymptote, but there'll be something like that. Yeah.
You're gonna have to graph any of the same asymptotes.
If I said slant asymptote will not be on your test, do you think you're going to have to graph any of slant asymptotes? No, definitely not. Yeah.
Would it be on the Alex?
I don't even think it was in Alex.
Oh,
If I recall, I mean, I looked through that section pretty carefully because chapter 4 had a lot of stuff I excluded and I tried to leave stuff off of Alex if we weren't going to go over it, and I don't think it was in Alex. Okay. What if that would have been slightly reversed? Like, what if it would have had an x squared in the top and an x in the bottom? Or an x squared in the top, and it would have been 2x cubed in the bottom. Then it would be 1 over 2x, and then as you plug in big x's, it would go to 0. Does that make sense? Those are the 3 cases. Either the powers are the same, the numerator's power is larger, or the denominator's power is larger, right? So, okay.
The one where you find the horizontal asymptote by dividing them and
That's oblique asymptotes, which is not going to be on the test, because those are slant asymptotes. You probably do that in calculus, though. All right, so this question A tripped a lot of you up because you didn't realize what you really have to do first is simplify the expression. Before you graph anything, simplify it. And when you simplify it, you're going to get out a really simple equation that you know how to graph. So how can this thing simplify? By factoring x plus 3, x minus 3. And how does the denominator factor?
3 times x plus 3.
Oh, look, somebody tried. Right? So how does that simplify?
X minus 3 over 3.
And the one technicality is x cannot equal -3. Why is there that technicality? Because the original function has a denominator and you've got to account for that restriction. Okay, now this thing. Don't fail me now. Divide both pieces by 3. It's 1/3 x minus 1, right? This is a fancy, disguised way to write a line. I could have asked my Algebra 1 students to do this. Okay? So don't let it be beaten by algebra 1 students. Where does the line start?
Negative.
-1. And also what I found to be kind of helpful is I told my students to draw in a vertical line at x equals -3. This is not an asymptote, so I'm not trying to like confuse you and think it is, but when you cross that vertical line, that's the point that you leave out. But other than that one little thing, there's no difference between graphing this and graphing a line with y-intercept -1, slope 1/3. You go up 1 over 3, right? Or down 1, backwards 3. And when you cross that vertical line, you leave an open circle because that corresponds to the y value where the x was -3. And that's the one number you can't plug in. This is a line with a hole. Does that make sense? Okay. So if you can simplify, do so. Just watch out for killing kittens, for lack of a better way. Can this next simplified at all? No. Okay, so this one, start by finding the vertical asymptote, if there is any. X equals 3, right, sketch it in. Horizontal asymptote, y equals largest power over largest power, y equals 2. And then your fallback method, if you're stuck, is to plug in x's, get out y's, right? And the only tricky thing with these things is that you gotta plug some numbers that are on the left side of the vertical asymptote and on the right side of the vertical asymptote, because stuff could change at that asymptote. So, okay, so we got x, we got y. So I think 0 is awesome, right? When you plug in 0, what do you get for y? -1. And then you can plug in whatever you want, but I would try to choose stuff that gives you whole numbers. I think when you plug in 2, you get a whole number. You don't have to, I'll try to make, if I give you a question like this, I'll make it so that that actually happens. So would that be, the numerator would be 7, right? What would the denominator be? So that would give you, so over 2, down 7. So you know, you're kind of like there-ish. Well, what's a good number to pick on the other side? One number past 3 would be. Does it make sense that picking one number more than 3 guarantees your denominator is 1? So I think that's going to be 11, which I'm well aware is off my grid, so just that 7, 8, 9, 10, 11, just, you know, do the best you can. I'm not going to, it's like music where you go above the staff. I played the flute, so that happened all the time. All right, I think plugging in 6 works out nicely. So that's 12, I think it's 15 over 3. Do you guys agree with that? So that's 5. Not awful. Yeah, you're asking if you can use symmetry to figure it out. The answer is yes. Yeah. There is some relationship between how those points are related to each other. So yeah, like that first one's 1 away from the asymptote, 1 in the other direction.
Well, because couldn't you just like, if you cut this in a piece of paper, couldn't you just fold it together?
Yeah, there definitely is reflective symmetry in this picture. That does depend on the fact that it's like a linear function over a linear function. Like if I would have thrown squares in there, it would mess that up. Does that make sense? So for the simple cases, yes, there is some symmetry. All right, and there was a whole bunch of graphing and transformations and stuff. So, woo. So what do you start with? What's your parent function? Square root of x. Goes through 0, 0, 1, 1, 4, 2. And then what do you do to that function? Shift it left 5 and This one doesn't officially have any asymptotes, like there's no lines it approaches and gets close to, it just has a terminal point. So left 5, 1, 2, 3, 4, 5, 1, 2, 3, down. Okay, there you go. How about, can I go to the next one? Okay. How about this one? You take the function that's e to the 2x, and what do you do to it? Shift it down 4. All right, e to the 2x. Well, what's a good number to plug in? 0. When you plug in 0, what do you get out? 1. So you go through that point. What is e approximately equal to? 2.71. So if you plug in 1, you get e squared, which is about 2.5 squared, 3, so what's that approximately?
A little under 9.
I think it's actually about, so you can actually, it's a little above 5. Yeah, so 5-ish. Like, I'm just checking if you know about where it is. And the general shape of that e to the x function looks like that. And this one does actually have an asymptote. It is the x-axis, right? Before it's been shifted, that is. I'm going to take that thing and shift it down 4. So the first thing that I would shift is that asymptote goes down 4. So the horizontal asymptote is now at -4. Goes through the point 0, -3, and then 1, 2, 3, 4-ish.
So how did you know that asymptote was there?
Because we talked a lot about what e to the x looks like. And so if you take the function e to the x and you plug in negative numbers, you get e to the -1 is 1 over e. E to the -2 is 1 over e squared. And as you plug in negative x's, these numbers get smaller and smaller and closer to 0.
Oh, okay.
The one we did it specifically with really was 2 to the x, because then when you plug in negatives, you can conceptualize that, okay, 2 to the negative first is a half, and then a quarter, and then a 16th.
I prefer to plug in a half for the x, so I get 2.7.
Oh, that works as well.
So then I don't have to square it.
Yep, that makes sense. Okay, let's do this one. So 2 plus e to the -x. So what does this negative inside the e, what kind of reflection does that do? Flip over, it's not the x, it's flip over the y-axis. So here is regular e to the x, looks like this. Here's what e to the -x looks like. And what does the +2 do to it? Moves it up 2. And so there's a horizontal asymptote at 2. Okay. I know I'm going to go just a tad over. Let's just do the log function, okay? Because I know it's going to be a tricky one. Yeah.
What does a fraction of the exponent
That's going to shrink the graph as opposed to stretch the graph. Was the 2x made it sort of taller? If I did like 1/2 x, it'd make it shorter. Okay, one more. So I need you to know what natural log of x looks like approximately. This is the inverse of e to the x. So e to the x looks like this. You obtain the inverse by flip-flopping the x's and the y's, right? So that first point is, looks like it's 0, 1. When you flip-flop, it becomes 1, 0. So right there. And this point is 1, 2.71. So when you flip-flop, it becomes 2.71, 1. So it looks like this. You have to just kind of know that's what that picture looks like. The original picture had a horizontal asymptote, this one has a vertical asymptote. So that is the basic graph of natural log of x. If you have to flashcard it. Because once you know that, can you shift it? Yeah. And this one was a bit tricky because I threw a lot of things in there. What does this negative do first? Flips it over the, oh, nope, over the x. And then once you've been reflected over the x-axis, how do you shift? Left 2 and up 5. And you have a vertical asymptote at -2. So, all right. So I'll postpone the